Alrighty, y'all. Today we're taking a look at the recitation for February 23rd. Right? In this one, we're going to be practicing more with some free body diagrams and breaking things into components, right, based on our coordinate system. Right? So we have a penguin sliding down a hill, and the first thing I'm going to do, we're going to draw a cartoon of our problem. So I'm just going to draw a penguin real quick. And there he is sliding down a hill. You know that hill's at some angle theta. Right, and then sliding down an icy hill, and now we're going to label our coordinate system. Right, so for this one, we're using our regular coordinate system where say that's positive x and this is positive y. Right, so now I'm going to draw our force diagram for the penguin. Right, so I drew a lovely picture of a penguin before, and there's a also lovely picture of a penguin. Right, so we have gravity acting down, and if I just have, here's our slope that our penguin's going down, just for reference. There's our force that's normal to that. Right, so we know that we're going to be looking in our x and y coordinate directions, right? So I'm going to break our normal force into x and y components so we can do a sum of all forces in those two directions. Right, so if I draw our normal force vector, and here's our x component, here's going to be our y component, right? And the way that our theta works, right, if this is our theta down here, this is going to be our theta here, right? If we do all the geometry for it, this angle is going to be theta, this is 90 minus theta, this will be 90 minus theta, which is just going to be theta, right? So it's going to put theta for this triangle up here. So here's our Fn, here's our Fny, and our Fnx. Right? So Fny is going to equal Fn cosine theta, and Fnx is going to be Fn sine theta. Right? So our new free body diagram, our new force diagram is, there's our gravity, there's our Fny, there's our Fnx. Cool. So now that we have it broken into components, we can just use that trig and set up our Newton's second law for both directions, right? So we're going to get our sum of all forces in the x direction. That's going to be just our Fnx that's acting in the x direction. And so that's going to be our Fn sine theta, which is max, right? Because this is just the acceleration in the x direction. And now in our y direction, right, we have our normal force acting positive, so that's going to be Fn cosine theta plus gravity acting in the negative direction. This will be a negative mg, right? And that's our may, acceleration in the y direction. Cool. Now we got some stuff. So, but this, we have our two equations, right? But we have 1, 2, 3 unknowns, right? Because technically we know theta, right? It says it's an angle theta. That's a given piece of information. And also, we're going to assume our mass of our penguin is given as of right now as well, right? And then we know g, obviously. Right, so 2 equations, 3 unknowns, right? So now we have to relate our ax and ay, because as of right now, we don't have enough equations to solve for our acceleration. So we have to figure out how they're related. So if I go back to my original cartoon, right, we're going to say our penguin's accelerating down our slope, right? We know this. It's going to be trying to draw a little more parallel, right? Which means that if we're breaking this into our ax And AY, wow, what do you know? It's another trig triangle of vectors, right? And our theta is going to be there, right? Same thing, because if I drew this like this, it would be 90 minus theta, and then that's the opposite in our triangle, right? These are just our opposite interior angles on parallel lines, right? So we can say, if I steal this triangle and move it down to where we were just working, right? Here's our AX, AY, our acceleration. So I'm going to say A equals AY is A sine theta, and AX is A cosine theta. Okay. So now we have 4 equations and 4 unknowns, right? Because we had 3 unknowns, and then I introduced this new one that's just the acceleration. But I added 2 new equations, so it doesn't matter that I added that one new unknown, because it added the right amount of unknowns for our equations for our unknowns, right? So now we're going to have our sum of all forces, right? I'm going to rewrite that. So our Fn sine theta, right, is our m, and then our acceleration in the x direction was A cosine theta, and our in the y direction it was Fn cosine theta minus mg equals ma sine theta. But, oh no, Sydney made a mistake. Or did Sydney make the mistake on purpose to make a point, right? If we're keeping track of our coordinate systems, very, very important, remember? We said this was the positive x direction, but this is going to be a negative y direction, right? So really it's going to be a negative there, right? Because our acceleration in the y direction is going to be negative. So we have to remember to keep track of our signs. Very important, right? So now we have, in these 2 equations, we have 2 equations, 2 unknowns. Wow, it's almost like I planned this, right? So now we're going to solve these equations to find the magnitude of the acceleration, which, what a coincidence, that's just the magnitude of our acceleration. I'm not bothering to solve for these intermediate components. It's like an intermediate value that I'm trying to find. I'm not bothering to solve for the components and then get the magnitude. I'm just going straight for the magnitude. A little life hack for you there, right? So I'm going to hop on over here. I'm going to solve this equation for Fn just because it's a little simpler, right? Normal force is going to be ma cosine theta over sine theta. Now I'm going to plug this in for Fn over here, right? So it's going to be ma cosine theta over sine theta times, that's not a sine, that's a cosine, right? Minus mg equals negative ma sine theta, right? Cool, wonderful. Now, fun trick, every term has the mass of the penguin in it. So remember I said that we were ignoring the fact that we technically didn't know the mass yet? That's because we didn't need to know the mass of the penguin just yet, because we don't need to know the mass of the penguin, okay? So now we have a cosine squared theta over sine theta minus g equals negative a sine theta. And I don't like how we have this sine theta in the denominator, so I'm just going to multiply through by everything multiplied by sine theta, just for the sake of simplicity, right? So a cosine squared theta minus g sine theta equals negative a sine squared theta. Cool, wonderful. Now our end goal is to get the acceleration of the penguin, so I'm going to get all the terms with a isolated to the same side. So it's going to be a cosine squared theta plus a sine squared theta. All right, and I'm going to pull a g to the other side equals g sine theta. I'm going to factor out this acceleration. So A cosine squared theta plus sine squared theta equals G sine theta. And wow, what a coincidence. Cosine squared plus sine squared, who remembers pre-calc with our unit circles and our trig identities. Yeah, we love trig. We love the unit circle. Everything's wonderful. But cosine squared theta plus sine squared theta is 1, right? So we're just multiplying by 1. This whole section goes away. Yet acceleration is our G sine theta. Cool. I mean, it took a little bit of trig and a little bit of mess and figuring out some vectors and stuff, but we got to a nice simplified answer. Not bad, not bad. It's almost like I know what I'm doing, right? So now we're going to do this problem again, but this time tilting our axes, tilting our coordinate system. So I'm going to steal my same picture of a penguin. All right, so we're drawing our cartoon of the problem. The picture is going to be the same. The only thing that's different is how I'm setting up my axes now. So now instead of using our up and right, I'm going to take these. I'm going to say, there's my positive x, there's my positive y, right? And we're keeping the axes perpendicular, right? Same thing as always, like, so if we had our components, we can just Pythagorean theorem and get a hypotenuse, keeping everything with our right triangles, right? This is how we're going to set our axes, right? So now we redraw our force diagram, right? It's going to look very similar to the last one for the first part, right? There's our gravity. And here is our slope, right? The slope is not a force on it. I just mark that, and I mark it with a dotted line. So I can see that, right, since it's a normal force, it should be normal or perpendicular to that slope. That's all that's indicating, right? But now instead, right, before we wanted to break up our normal component so that it was parallel and perpendicular to our axes. But now since our axes are tilted, our normal component is already in line with our y direction, right? Because this is our y direction now. This is our, that's crooked. This is our x direction, right? So we want to line up everything with these two axes. Our normal force is already going to be perpendicular to our surface, right? As I was just saying, normal means perpendicular. So this time we have to break gravity up into two different components, right? So here's our gravity vector, right? And we want a, if I draw our slope again, just real quick to see. All right. So we want a this way component, and we need a this way component. Here's our right triangle. All right, and if we do a little bit of an angle evaluation, right, there's our theta, right? So our theta is going to be, right, we're going to move this over here. Theta is going to be here, which means theta is here, right? So now if I just redraw this triangle real quick without all the extra markings on it, we have gravity, this way direction, and this way direction. And a very, very important thing to remember is that whenever we're breaking a force into two different components, right, we're breaking them into this way component and this way component. The components are always going to be the legs of our right triangle, right? See how I set that up? Those are the legs of our right triangle. Our component our vector that we're breaking into components has to be the hypotenuse, right? Because when we add x and y direction, they're going to sum to our regular vector, right? But if I added our actual vector and this y direction, it's not going to sum to that. It's going to be different, obviously, right? But that's a very important thing to remember when we're breaking something into components. No matter what direction components we're looking at, our vector is going to be the hypotenuse of our triangle, all right? So, like, technically a legal triangle, right? I said this was here, and I wanted our right? If I'm saying I want, here's our slope, this way direction. There's our full slope, actually. If I want the this way direction and this way direction, right? It looks like it could be fine like this, but really, in this case, we wouldn't know the magnitude of this as a leg because it's weird, and now suddenly this is our FG. That's now a leg of a triangle. This is very, very illegal. Don't do this. Crimes. It's not very illegal. You could, don't do this. This is not going to give you the right answer. The secret is make it the hypotenuse of your triangle, right? So now we're going to have our FG in our x direction, right, which is this one. That's going to be our FG sine theta, and our FGY is our FG cosine theta. And another thing, right, a lot of times will want to use just like the general rule of, right, our x, oh, that's the sine direction, right, because from our unit circle, x was the sine of that angle, but it depends on where we're measuring the angle from. So you really always have to set up your triangle, find your theta, and do the trig, right? We're not going to be doing any shortcuts and whatnot, right? So I'm just going to, like I did before, I'm going to redraw my force diagram just with these components, right? So that's our slope. And now we have, right, our normal force, which didn't change. And now we have our force due to gravity in the y direction and our FGX. Okay. And a little fun trick for this one, right? If I just took this and I tilted it, like, because that's what we're saying is we're tilting our axes. If I tilt it back, that looks almost exactly like our other force diagram, right? It's just in x and y directions. The only difference is we're not looking at the horizontal. This is really our horizontal here. There's our theta, right? Little secret, but this is the way we're visualizing it now. We're just the same way we can pick an origin. We can pick how we set up our axes. We can pick which direction's positive, right? It doesn't always have to be, right? We always say we can pick which direction's positive. It doesn't have to be up and right. It can be that way and that way, right? But we want to keep them perpendicular to each other. Okay, so now we're doing our Newton's second law, right? I skipped ahead a bit and did the trig already, right? It's just easier to look at the geometry when we're looking at the geometry. So now we're going to say our sum of all forces in the x direction, right? That's just our FGX acting in that positive direction. So FG is our mg, so that's going to be mg cosine. Ooh. I did the problem. Mg sine theta. There it is, right? Mg sine theta. Ooh, Sydney made another mistake. What did she do? It's going in our negative direction here. Right? So we are MAX. Right? I do our sum of all forces in the y direction. I made that mistake on purpose, I promise. Right? In our y direction, right, we have our normal force acting positive. So our Fn, okay, plus, because we're adding, it's always the sum of the forces, we're adding forces. But our FGY is a negative, so it's going to be plus a negative, which means it's just going to be a negative. So that's going to be our mg cosine theta. And that's going to be our m. Cool. So now we're back where we were before, right? We have 1, 2 equations and 1, 2, 3 unknowns. But, little secret, not a secret, this is just what we're doing, right? If I pull these on down here, right? What do we know about our penguin's motion, right? Our penguin isn't accelerating this way, right? It's not jumping up off of the slope. It's just accelerating down the slope, right? So that means that our y direction of our acceleration for our penguin in this direction is going to be 0, right? So we can literally just say our AY is going to equal 0 meters per second squared. Suddenly this whole term disappears, and we're just saying that. Now we have 2 equations, 2 unknowns. Okay? So now we solve the equations to find our acceleration of our penguin. And it's actually pretty magical because we don't even need the second equation, right? Since there's no normal force in here, we can just say, right, if I divide out by m again, right, AX is our g sine theta, right? And since we said our acceleration in the y direction is 0, right, to find our magnitude of our total acceleration, right, I have the x component and I have the y component, so we add them together, right? If it was Pythagoras theorem, it would be 0 squared plus g sine theta squared. Take your square root. 0 is just going to disappear. Square root of that is just going to give us, right, our acceleration is just our g sine theta, right? Right, you can do this without the Pythagorean theorem and just say, since AY is 0, this is just going to be our acceleration, but that's just the reason that it's like that, right? Which works out wonderful, right? So here's our A equals G sine theta, and that's what we got before as well, A equals G sine theta. But this one took more than a few less steps, right? The differences between the two approaches was just our frame of reference, right? What we broke into components and how easy we made the math on ourselves, or the algebra, right? So we aligned the coordinate system with the direction that we knew the penguin would accelerate in, right? That's kind of like what we were doing for like kinematics and projectile motion, right? We said this, we aligned our axes with the way we knew things would accelerate in because our G was just acting up and down in the y direction, right? We did the same thing as before. It's nothing new. We're just defining that we can move our axes now more, right? We aligned our axes with gravity, the way we knew that things would accelerate in during free fall. Now we're aligning our axes with the way we knew the penguin's going to accelerate, just not in free fall anymore, right? So that's generally it. The tilted axes. The moral of the story is that our tilted axes are going to be easier for that penguin, right? So now we're going to have 2 masses on a frictionless pulley. And just for the fun of it, I'm going to label this one as M1 and this one as M2. Doesn't really matter which one's which. We'll be figuring that out after, right? So what do we expect the system to do if one is much heavier than the other? And what do we expect it to do if masses are equal? Well, if this one, right, it looks bigger, so I'm going to say this one's a lot bigger for right now, right? So if this one's a lot heavier than this one, it's going to fall this way, right? And it's going to fall pretty fast, right? But if they're equal, they're just kind of like balance out and not really move at all. So that's kind of what we're thinking about, right? If we had something just like on a pulley, balanced like that, that's what we expect to happen. So let's see if it works out with our math and stuff, right? Sum of all forces. Spoiler alert, it will, but it's, right? So I'm going to start with our force diagrams, right? Same thing we've always been doing, right? Our M1, here's our mass 1, and here's our FG1, and here is our tension in the rope, whatever's pulling it up, right? And now, let's move that over a little bit. So now I have space to do M2, right? So now we're going to have our FG2, right, and our, it's a gross looking arrow, tension in the rope, right? Same thing. The only thing that's acting on it is gravity and the rope that's holding it up, if it's holding it up, right? So, right, we have to set a coordinate system. Right, we said we can set whatever our coordinate system is for whatever we want. So I said, just for an example, M1's going to be heavier. So I'm going to say the direction I expect M1 to accelerate in is down. That's going to be my positive in the y direction for my M1. Just deciding that. Right? Same thing with M2. I expect it to accelerate up because I'm just assuming for right now that it's going to be the smaller one. Right? So I'm going to say that's my positive for M2. Right? And I can do this, right? I can set a different coordinate system for each of my things as long as I remember how their motion is like relative, right? So I'm not going to say that, right? I have to think about, just have to think about like what direction they're going in relation to their own coordinate systems, right? So now we do our Newton's second law, right? So we're going to do our sum of all forces on number 1 is, right? And I said my FG is in the positive direction. So that's going to be M1G plus a negative tension, right? And that's going to be M1A1, right? And we can do the same thing for our mass 2. Moral forces on number 2 is, right? Acting in the positive direction is our tension plus a negative FG2, right? So that's going to be negative M2G, right? And that's going to be our M2G2. And notice I didn't subscript our tension, right? Because we're given that it's a light frictionless pulley, all this stuff, we're going to say, right, and it's right over here, the tension forces are the same, right? Just the tension in the rope, it's the same no matter where in the rope we are. So it's pulling up on this one is the same force it's pulling up on this one. Okay, cool. So now we have 2 copies of Newton's second law. And we have 1, 2, 3 unknowns. Wow, I'm sensing a pattern that this has happened multiple times in this recitation, right? So what we do now is we think about how our accelerations are in relation to each other, right? However fast this one is accelerating down, right? Again, because I'm saying this one's the heavier one for right now. However fast this one's accelerating down, that's going to be the same magnitude as how fast this one's accelerating up, right? And if this one was the heavier one, this one's accelerating down with the same magnitude acceleration as this one's accelerating up. If I had set the same coordinate system for both, which is perfectly fine, we just have to think about that here, right? Then whatever acceleration this one's going down in, so negative A, would be the same as this positive A, right? But since I said that they're opposite directions, their accelerations are just going to be the same, right? So that means that A1 equals A2, and I'm just going to use, so I don't have to think about the different subscripts, I'm just going to use just a general A for that, right? So I can say those just, wrote G. I was not supposed to do that. A2, sorry, G doesn't change. Our acceleration of number 2 is what can change. G is not going to be different for each of them. My bad. My brain just didn't wake up just yet, right? But either way, we are saying that's equal to this variable A. So now we have 1, 2 unknowns within our 2 equations. Wonderful. Now we can solve for what's going on, right? Let me just get rid of this to make math a little bit simpler looking. So we have 2 equations, 2 unknowns, and now we're solving for our acceleration. Okay? And it says solve for A1 and A2, right? I said A1 and A2 are both equal to A, right? Because that's how I set up my coordinate systems to work, and I'm allowed to do that. So I'm saying they're equal, and they're just going to be equal to this. So when I solve for this, that's going to give me A1 and A2, right? So first thing I'm going to do is solve this one for tension. Right, so we're going to say tension equals M1G minus M1A. Okay, and I'm going to plug that tension in over here. So you get M1G minus M1A. Right, tension. That's, I don't know why I wrote that, but there's our tension expanded out. Right, and then minus, we just rewrite the rest of the equation, equals M2A, right? Now I'm going to start simplifying this, right? Since it's all addition and subtraction, I can just open those parentheses. I'm going to do the same thing I did before and get all of our acceleration terms to the same side. So m1g minus m2g equals m2a plus m1a. I factor out my a. Actually, I'm going to switch the sides because I want to have what I'm working with on the left side. That just makes it easier for me to think about. Doesn't matter which side of your equation it's on. It's just for my own thought process, right? So we're going to factor out that a, m1 plus m2, right, equals, I'm going to factor out a g over here too. Why not, right? m1 minus m2, right? So now if we divide, our acceleration is going to equal g m1 minus m2 over m1 plus m2. Wonderful, right? We have an isolated equation giving us acceleration in terms of the masses. Now we get to think, right? Does it agree with our predictions, right? So let's say that our mass 1, like we were thinking about before, say our mass 1 is much bigger than our mass 2, right? Meaning that whatever this is, right, if it's very small in comparison to what this is, we can approximate and say, well, if M2 doesn't really matter in the grand scheme of M1, we can just kind of like, we can just kind of like ignore it for right now. It's going to be M1 over M1. And our acceleration is going to get pretty close to like G, right? Because that's just going to be, it's going to be pretty close to G in that positive direction, because we're saying this is our positive direction, this is our positive direction. If this is if there's no mass on this side and this is just fall, and that would mean this was just in free fall, right? Because the tension the tension would be 0 at that point, right? Because there's no mass on the other side to like counterbalance it at all, right? So this makes sense. Wonderful, wonderful, right? Now, if M2 is much bigger than M1, right? We can say the same thing, right? Suddenly M1, the mass is negligible compared to, right? If M1 is 0, right? Suddenly we have M2 over M2 in the negative direction. Our acceleration is going to be pretty close to our negative g, right? Not pretty close, right? If M1 is actually 0, our acceleration is going to be our negative g for this, right? Which makes sense with what what we were thinking, right? Because if M2 is suddenly a lot bigger, now we're accelerating this way, right? Same thing we were saying before. Our acceleration is going to be just like this was in free fall because the tension's not there, right? But we're accelerating this way. And we said that was negative for both, right? That makes sense, our negative acceleration, right? 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 And it's the greater the difference between the masses, the closer it is to G, right? And it makes sense that we're seeing this, right? Because this means that our larger mass is always going to be accelerating down, whether it's negative or positive for how we set it. And our smaller mass is going to be accelerating up, which makes so much sense. So, good job, good work. I'm so proud of you. We got a functional equation for our acceleration, and it makes sense. We're not going to break the universe at all. All right, well, I hope you found this at least a little bit helpful. Let me know if you have any more questions about this recitation, or if there's any other problems that you want me to try to explain, and I'll do my best to try to explain them, because I guess Sydney explains stuff.